Okay. So let's see, 2D vectors resultant and let's see, equilibrant. Yes, these are the two things that we are going to be looking at uh, as far as what? As far as the resultant is concerned, not only the resultant, but also the equilibrant. So, very quickly, let's have a look at that definition over there, where this talks about the resultant. What is the resultant? It is just a single vector which has the same effect as the original vectors acting simultaneously on an object. So it is that situation, if you remember, whereby you've got a boat going in that direction and then from there continues to be in that direction. So when one comes, it is still the same as it having moved from there to there. So you've got 1, 2, which can be represented by a single vector. And you see, still having the same effect because it has just moved from that point A to that point. It could be point C because it went there to there, but to a, let's say, the end point. Yes. Okay, worry not. We will therefore continue to talk about the equilibrant. The equilibrant, which is the force. What? The force. So now we are being specific to say we're talking about the force that keeps a system in equilibrium. Maybe a practical example would be, maybe let's say we have what is it? Okay, let's say this is a ceiling. We have a cord that is holding a projector there, something of that nature, honorable member. So you can see that force is being applied to keep this system in equilibrium. So it is this cord, as a result of that tension, keeping this projector in that position. So this, it is what they are talking about. It is the one that keeps the system in equilibrium. Therefore, that type of a force would be the equilibrant. So the equilibrant is equal in magnitude, but opposite in direction to the resultant force. Yes, I think this one makes sense, honorable member. Like I was saying, obviously, this object, because of the weight, it wants to go down. Nay, if the weight is 100 Newton, this force is being applied, but look at this, in that direction. And it has to be equal to that one so that the resultant will be zero. It's like you're having a positive force and a negative force. If you combine them together to find the resultant, you will find zero. So that's why this object is like, it is just there at equal force being bigger than the upward force, something of that nature. That's what keeps it in equilibrium. So maybe another example would be an object which is on a table, whereby as a result of force by gravity, it is exerting a downward force on that table. The table itself, it is applying that equilibrant force or a force which is in the upward direction at the same time being 10 Newton. That is why this object will just remain there on the table at equilibrium. Nothing is moving because the two forces are balancing, the other one up, the other one down. Same magnitudes, but in opposite directions. That's what that statement means over there. Okay, here's a quick one, honorable member, where we talk about the Pythagoras. Nay, the Pythagoras only applies definitely when you are having a right-angled triangle. And you know the formula most. And again, with regards to finding the angles of a right-angled triangle, it could be the angles or the sides. You know the formula most. So Katoa. This is what you find in trigonometry, of which we have dealt with that. Okay, so now they're talking about an example there where a boat travels a 90 meter due east that we can see, and then again moves a 50 meter due north. Okay, now they want you to determine the displacement of that boat. Most importantly, displacement is a vector quantity which has both the direction and not the direction, but the magnitude and the direction. Yes. So now, obviously, the resultant, it is definitely that one. I think this example, it was explained in the previous example, whereby we are definitely going to use theorem of Pythagoras. Why theorem? Because this is 90 degree and this is a right angled triangle, where this is the formula. Definitely you substitute one side, you square both, and then remember, or you square each, and then remember you'll say square root of that so that you can find that, whereby you end up getting that. So that means this is that distance, the resultant being that meters. Okay, so when it comes to the angle, honorable member, definitely we are still on a right angled triangle, whereby if you have the opposite and adjacent, because this side is opposite to that angle, this is adjacent to that angle, you definitely will use tan because it's opposite over adjacent, where you substitute and then you say shift tan that, and this is the angle that you get. So this angle, it is actually that one of 29.05 degrees. But most importantly, in physical sciences, the direction we easily measure by the bearing. What is the bearing? So very much important, honorable member. This is just a reminder to say that angle that you calculated, this one, it is with reference to the x-axis, which means it is from the x-axis to that resultant. So when it comes to the direction, we talk about the bearing. So now what is the bearing? The bearing is measured from the vertical axis or the y-axis to where the line is. So if that line is like that, then the bearing is from there to wherever that line is, which means in this case, we are having a 90 degree there, and this angle, we've just calculated it to be that 29.05 degrees. So to get this angle, it will therefore have to be that 90 degrees minus that angle theta of 20 wara, so that we will remain with this angle, and that angle, it is what we call the bearing. So imagine, for example, if maybe we had the boat or the resultant in that direction. So that would mean in terms of the bearing, we might need to do that and say the bearing was therefore with reference to that y-axis or the north. It will have to be the whole of this angle, where you are having that 90, you plus it with that extra angle. So that means that that extra angle, you can calculate it by just focusing on this smaller angle, which is reference to the x-axis, and then you will plus it with that 90. So that gives you a bearing, which is that whole angle. Otherwise, if the resultant was like that, it would be a 90 plus 90 plus that smaller angle. Therefore, that would be your bearing. Yes, something of that nature, honorable mem. So it's like the bearing will be that angle which is measured from the y-axis in a clockwise direction. Yes. I hope that part makes sense. So now let's get to this example, but definitely before we get to the example, very, very much important, honorable member, that you know, we talk about what is it? The sine rule. So the sine rule, it focuses on where you are having a non-90 degree triangle. Maybe let me just quickly redraw all of that and start you from scratch, because this teaching you find in a trigonometry lesson, whereby if you have a triangle like that, maybe this is A, maybe this is B, this is C. As long as this angle is different from that one and is different from that one, then you can see we are not having a right angled triangle because the inside angles are different. So this is what the formula says, honorable member. You see this angle, which is opposite to this side. This side is small letter A because that point is capital letter A. So if this angle, it is therefore opposite this side we'll call it small b because that point is capital letter B. Similarly, with this one, that means it will be small letter C. So the formula says if it is the side or the angle, it doesn't matter what you're calculating, you can use these formulas. So let's say it is the side that you are calculating. The formula says that side A, you just divide it by sine of that angle at A. And this is equals to that side B. It can still be equated to that C over sine of angle C. So it just depends on what you are given in terms of whether to take this equated to that, or take this equated to that, or take this and equated to that. It depends on what you are given. Otherwise, if it is the angle that you are looking for, then that's when the sine A comes to the top, it becomes the numerator, and then A to the bottom. And then you just swap. Same formula, is just that this time around you are swapping. That's it, honorable member. Not that much complicated, not that. Yeah, I think I wanted to say, yeah, I think I need to just, is it taking a sip or what? I'm having ice cream on my side. Yeah, I think I need to warm up my throat. No, not to warm, but to, is it to cold it? Yes. Something of that nature, honorable. I don't even know what I was trying to say. But otherwise, it's fine. Not that much is difficult, not that much is complicated, but yes, you just do it that way. I think this formula, you will understand it better when it comes to the topic for trigonometry. I think I will have to include that part because this part of physical sciences, it goes hand in hand with trigonometry. The trigonometry, yes, maybe part of trigonometry that deals with this type of triangles, where you use the sine rule. Okay, then it's fine. Let's go back to the example that we will need to deal with. So you can see that what I've just explained, it was the use of these formulas with reference to that type of a right angled triangle, where you are having here, they are using it as angle, capital letter B, angle, capital letter C, angle. The side will be that, and that. Doesn't really matter that much in terms of what letters you use there, whether you use the angles and the points, etc., still fine. So let's look at that example, honorable member. Maybe because I'm having that diagram on the other device, I'll just have to redraw it as I explain. So at least you will have an idea of what's happening there. But maybe let me start with reading the question itself, where they say, it is an object which is suspended from a ceiling by two cords, as shown in the diagram below. What they want you to do is to determine the magnitude of tension 1 and tension 2. Okay, then it's fine. It's fine. So this is what's happening. So you can be having that nice house there. And then you have the ceiling, definitely. And then you have this object being held by those two cords, where this is tension 1, cord 2, having tension number 2. Yes, something of this nature, honorable member, whereby there are angles formed. So there is that angle, and also there is that angle. This one is what? I think it's 60 degrees. This one is 35 degrees. Let's see, where is that? 60 degrees, 35 degrees. Yes, we're just saying the angle formed between this chord and also the ceiling, and also the one formed by that and also that. Yes, those are the angles which are measured. So I'll just have a schematic representation of that, whereby we can see now this is that ceiling, and then we are having this chord, and then we're having that, even though it's not drawn to scale, but I hope you've got an idea there. And they're saying this object is 3 kg. and then that is 60 degrees, and then that is that, and then this is chord 1, and then this is chord 2. That's why tension 1, tension 2. Okay, then it's fine. Most importantly, honorable member, it is a free body diagram that you will draw, which will assist you to do a better interpretation there. Definitely, we will be having the weight, and the weight is calculated obviously using the formula FG. We know FG is equals to mg, isn't it? Mass times acceleration. The nice thing about this is that the acceleration doesn't change. It is always 9.8. That is the gravitational acceleration, or the acceleration as a result of force of gravity. Whereby the mass we just said is 3. So that means this 3 is the one which is multiplying that 3.8. We end up having what? Let's see. 3 times 9.8. What did I say? 29.4, yes. So 29.4, most importantly, Newton. That means it is the weight of that, it is the force as a result of that mass of 3 kg. So this 29.4 is the weight of that object. Okay, then it's fine. We've got this one for the tension number 2. And remember, the angle that is formed there, it is that one that was measured to be, what was it? 35 degrees. So you don't need to show all this when you're drawing a free label. That just wanted to remind you there. Then you have this one in that direction, which is tension number 1. So very, very much important. The labeled free body diagram will therefore have those arrows to show the force or the direction of the force, and you label those forces. So now when coming to part, it means we are going to have to do a manipulation, which is a manipulation of this, where we now draw, what are we drawing? Where we draw a force triangle. That's how we can easily manipulate it. Okay, I think let me do this and say, take a screenshot and see if you can be able to work out this on your own. Take a screenshot and then I'm going to disappear just now.